My name is Professor Raman Prinja. I'm an astrophysicist, but I'm also here because I'm the head of department. And it's a delight for me to welcome you today to this department. I want to start by congratulating you. You are offer holders, and that takes some achievement. You've achieved already something. You've got an offer from this department. That offer would have taken years of scaffolding to achieve, and we're very respectful of that, and so I want to congratulate for that. So here, we're offering you now a chance today. We're welcoming you here because we've built here a chance for an in-depth, tailored view of life in this department. That's what you're going to get to experience today, and I hope you really get to enjoy that and get a feel for what this department's about. The key thing, though, is relax. Just chill, right? It's okay. It's going to be good, right? So you've got a chance here today to meet with some of our current undergraduates, our postgraduate students, and they'll give you the real lowdown. I mean, ask them stuff, right? They'll give you the real lowdown on this department. It's a great department. And then you'll also get a chance later on this afternoon to have a one-to-one chat with some of our academic staff members. And I emphasize it's a one-to-one chat. This is not an interview. You've got your offers. This is a chance to find out about this department, find out why you really want to come to UCL, because I know you really want to come to UCL. So that's what you want to do here, okay? The key thing here also is that I hope you will get this opportunity, use this opportunity today to also get an experience, essentially, of the link that we have between our teaching and our research. This is a research-dominated department that is extremely serious about its undergraduate and postgraduate teaching. We have 5 outstanding research groups in high-energy physics, in atomic molecular positron physics, in astrophysics, in biological physics, and in condensed matter physics, right? That sounds like a lot of physics, but that's why you've come here, for a lot of physics, right? All kinds of work is done here across the whole spectrum, from studying of nanoparticles to surveys of galaxies and cosmology. I mean, that's wide. From measuring forces on individual cells in your body to trying to detect the biosignatures in the atmospheres of these billions of exoplanets there are in our galaxy. It's all happening here, right? And you got a chance to meet some of the people who are doing that stuff today, but also to understand that we are looking to embed in our education the research elements that we have from these groups, right? So right from the get-go, from the early years, we will try to engage you within our research groups. And as you move through the years, you will see, and you can ask about it today, that as you move through and you come to the 3rd years and the 4th years, the final years, you're firmly embedded and connected with our research groups. But the opportunities will be there from the start, okay? So I hope you get a chance to get a feel for that. The other thing is, it is a department of opportunities. I'm here as head of department, but this is a vibrant department, right? It's really a vibrant department. I hope you get a feel for some of that from me today. And it is an department of opportunities. Yes, you have this opportunity to have a first-class education, first class leading to first-class degrees, right? It's all linked, you know, it's all worked out, right? First-class education, opportunities to engage with research, but then beyond that, there are other opportunities you can have in this department in terms of innovation, right? Group work, transferable skills for industry. We have a fantastic employment record in this department. Careers built, the advice for building careers on that. And in addition to that, opportunities beyond that, for example, in terms of outreach and public engagement. Some of the people who are going to be guiding you around today, some of the postgraduates and undergraduates, are going out into schools to deliver outreach, our outreach mission, right? So you'll see that there is this wide spectrum that you can achieve in this department as you come in. There's a lot of interconnections between what we do, right? In the research, in the techniques, in whatever we're doing. So I hope you'll get a feel for that as well. Finally, I want to emphasize also that one of the other things we're extremely proud of in this department is that we are sold onto the mission of equality, diversity, and inclusion. We believe in that mission completely, as is the university. We are Juno champions. We have awards for that. We are part of the Athena Swan scheme. And for us, respect and diversity inclusion is in our DNA. Right? That is what we are about. And that will be always the case for us. And you can have that assurance from us, both of us, in that respect. So I think that's it from me. I'm really glad to have had this chance to welcome you. I hope you have a great day here. I mean, get the most out of it. Honestly, you've come here, it's freezing cold, you've turned up, but get the most out of this. Don't shirk back. Ask lots of questions. Find out about us. You want to make an informed decision, right? That's why you're here. And you want to make the UCL decision. That's what you do. So I hope you have a great day. And thanks very much. And I'll catch up with you again later on.
Okay,
thank you.
Thank you so much, Roman, for your presentation. I'll take on from here, and I need your mic.
It's all yours.
Thank you. So, how does it go? Like this, I guess. So, hello, everyone. My name is Professor Carla Faria. I am the undergraduate admissions tutor, and I'm welcoming you here today. And I'm going to let you know what it means to study physics at UCL. Somehow. So, to start with, we have today not only the on-site students, but the first part of this open day is being streamed. And if you have any questions, hello you who are abroad, you can ask questions in this address. But if you are on site, feel free to ask here and make the most out of the opportunity. So welcome everybody. I'll start by telling you a bit about our history at UCL. We have a long tradition of being a very progressive institution. In fact, we have been grounded and founded on an entirely secular basis. We were the first university to admit women on equal footing as men. And you can actually read all that in these slides. I'm not going to go into detail, but the message to take home is that we have a strong commitment to being inclusive, to being diverse, and to being progressive. Also, we are quite a big department. In fact, we have around 600 undergraduate students. We have over 250 postgraduate students, over 100 postdocs, over 100 staff, and this means that we are very vibrant, we are a big community, and also we're not only good at research, we're also good at teaching. In fact, in the last teaching quality assessment, we have scored 23 out of 24 points, and we have been doing quite well on research as well. In the last Research Excellence Framework, we have been considered the second in the UK based on research intensity. This means quality and the fraction of the research active staff. We also have a lot of income coming from grants, which means that we can hire teaching fellows, and we have a very good staff student ratio, so you get a lot of attention. Also, if you join UCL, once you arrive here, you will be allocated a personal tutor who is an academic, and this person will be able to help you through your course, talk about career issues. Also, if you have personal issues you would like to ask him or her about, this is the person to go. And we have in our first and second years problem-solving tutorials. So we have the core classes. They are divided then into small groups, and you are given a sheet to try at home, and this is going to be discussed also with you afterwards by an academic. And what happens later? Well, later we are quite well placed as well, because 95% of our students, they find jobs actually at graduate level or go on to further study. It's really a tiny minority who doesn't find anything. And these, we are not even considering the people who find jobs which are not at graduate level. So actually you are quite well placed in employability as well. Talking about equality and women, etc., what you see is that 26% of our undergraduate students are women. This doesn't look like much, but is above the national average. And we have also that 1/5 of our PhD students are women. So if you're a woman, you're not going to be alone here. And we also have quite a few in leadership positions. So if you look at the staff profile, in the UK, as you can see, is not so good, but at UCL, we have quite a large number of women professors and also occupying leadership positions. So if we talk now about our research and teaching facilities, they are up to scratch. They have been upgraded a few years ago. And here on the left, what you see is the University of London Observatory in Mill Hill. We are going to hear more details about that in the afternoon when Dr. Steve Fosse is going to give you more information. This is mainly focused on outreach and teaching, but sometimes you can have a breakthrough. For instance, some years ago, some of our undergraduate students have found a supernova which was the brightest one in a decade when they were doing their project. So this can happen. Doesn't happen that often, okay? But it can happen. And here you have also the opportunity to see our teaching labs. So they have been refurbished, as I said, and in this picture, what you have is you have our research labs, an example of a research lab. And research areas here we have for all tastes, from the very applied to the very curiosity-driven. If you like to do theory, we have it. If you like to be more industry-related, we have it. And we have a lot in between as well. This is to give you an example of what is going on. We have 5 big research groups at UCL. And we also have a strong connection with medical physics and space science. So everybody here is research active, and it's very, very, very hard to get a permanent position at UCL, which means that the person teaching you is not only a teacher, but he or she is a researcher and is an expert and is working on a lot of fields and a lot of important questions. These are just some examples. For instance, they're investigating the Higgs boson, dark energy, dark matter, climate science, biophysics. This list is really, really, really non-exhaustive. So you will find world-class experts here. Also, we're quite a lot in the news. This is actually the supernova I was talking about. If you have a look, you see that the students, they spotted a bright light when they were looking. And after they ruled out all possibilities, they found out it was a supernova, the brightest in a decade. And there are some anecdotes about some people eating pizza or not eating pizza and missing it or not. I don't know. The person who really knows is Steve. You can ask him in the afternoon. But you hear a lot of stories, and apparently it was quite fun that they found it. They were really proud, which of course you are. Is very important. And Professor Raman Prinja was just here before me, our head of department. He's also quite engaged with the public. So he has written lots and lots and lots of books on popular science, on astrophysics, which is his area, but aimed at a broader audience. And You can Google him on Amazon, you find lots and lots and lots of hits. Also, this is a tradition because before him, there was a blog on The Guardian by our former head of department, Professor John Butterworth, which was Life and Physics. I think it just went on until last year, which is a pity, but he's still quite active on Twitter and he's actually quite viral. So this is his Twitter address and you can see a lot of things posting. And a lot of us have Twitter accounts. This is just to give you an idea. In fact, some of these people are professors here, some are students, some do outreach, some are working also towards improving the role of women. So this is just a variety, and if you like physics and you want to see what it means to be a physicist, you can follow some of them. Again, this is a non-exhaustive list. So to start with, I'm going to give you an example of research groups we have. So we have here a very active research group on high energy physics, and a highlight of this group is a connection with the Atlas experiment. So they are designing detectors at Large Hadron Collider to study proton-proton collisions and at very, very, very high energies. And this is a bombastic undertaking. It involves over 10,000 scientists from 50 countries. If you look at these, you see that everything is the largest in the world. It looks quite megalomaniac, but it's the truth, okay? And at the time, I remember that people were making a fuss that the world would end. I think the conspiracy theorists were getting a bit too obsessed. They're going to switch this off, and the world is going to end, and it's going to be a disaster. The world hasn't ended, and I think people were just making too much drama, but I mean, you can look at it also from the side that there's no such thing as bad publicity, okay? And I don't know why people make this drama, because we have high energy particles hitting the atmosphere all the time. In fact, one field of research that we have is to look at cosmic rays and neutrinos. And for instance, this guy is an example of someone who was at UCL. He did here his undergrad, then his PhD, and now he is in Antarctica looking for cosmic rays. So one thing, I mean, I see quite a lot of parents. I hope you don't worry too much, because one thing I'm going to tell you, and it is true, if you decide to become a physicist and you decide to do research, you're going to travel a lot, but really a lot, because you will go to conferences, you probably do postdocs in many places, your research involves talking to many people and collaborating with a lot of people, and you see the world, which is fun. Sometimes it's tiring, okay, but all in all it's fun, and you do see the world. In fact, if you come to UCL, you realize pretty soon that everybody here, or a big, big chunk of our staff and students and postdocs, they come from elsewhere. For instance, I came from the Amazon. In fact, I was born in the Amazon. I went to study in São Paulo. Then I moved to Berlin, did my PhD in Germany, many postdocs in Germany, came to the UK, and I got a permanent position at UCL. So I've been around, and we have all been around in one way or another. So this is a very international community. Science community is very international. Another group we have, and you have today the opportunity to see this building, is very close by, it's on Gordon Street. This is the LCN, London Centre of Nanotechnology, and this is a joint enterprise, UCL Imperial, and it's a dedicated center to study nanotechnology, to study nanostructures, and they have experiments and they have theory, and you see this building is very posh, has a lot of glass, and it's because there's a lot of interest from industry in nanotechnology. Because if you're working, for instance, with atomic and molecular physics, many times you have to use what nature gives you. And if you try to do something with nanostructures, you can tailor them to a specific purpose. So industry has quite a lot of interest in that. And today we're going to see a lab in the LCN. Another group which we have, to which I belonged, in fact, is atomic, molecular, and positron physics. So here in this picture, what you see is a positron beam, which was the first positronium beam in the world from Professor Nella Lariccia's group. So she has a lab on the 3rd floor. And we have, apart from that, very theoretical work, very applied work, a lot in between. And we also have a lot of connection with the LCN and with biophysics. So these are a few examples which you can read here. And in fact, my area of research is strong field and attosecond science. So I'm a theorist, and I work with the physics of the very, very, very strong and the very, 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 very small. Attoseconds, they are some of the shortest time scales in nature. And you can make back-of-the-envelope computation. If you take typical atomic dimensions, you divide them by the speed of light, you get something of the order of hundreds of attoseconds or attoseconds. So this means that you can, in principle, resolve an electronic wave packet which is moving in real time. You can resolve electron dynamics. You can make a molecular movie. And if you look at this picture, you see that everything else is there, right? In terms of what is happening and in terms of physics. Attoseconds are here. But all the rest is here. So it's really, really, really very, very short. It's extremely short and is a very transient regime. On top of that, I deal with very intense fields because to have this attosecond phenomena, you need to have the interaction of matter with very intense fields. And by intense, I mean intense. I mean 10 to the 14 watts per centimeter square or higher, if you look at the focused intensity. If you're wondering where you should stop putting your hand in front, I would say if you consider 1 watt is already pretty hard. Don't put your hand there, okay? So here I wouldn't put my hand already. But if you look, what you see is that if you look at this timeline, intensity that you can achieve with these lasers has moved up to a limit in which you can, in principle, I mean, it hasn't been achieved, but there are now facilities which are being built in Eastern Europe, which belong to the so-called extreme light infrastructure, which would allow you to do what you do nowadays with particle accelerators. You could do with them. Because, for instance, here, one expects, if you look at very, very, very tip, you see that if you would shine light in vacuum, and you could, in principle, polarize the vacuum and create an electron-positron pair. So you would be creating matter out of light. So strong this is. So you could do particle physics with strong lasers. And you see there's a long plateau in the 80s. And the reason why is because it was very difficult to achieve these intensities. And in fact, last year, there was a Nobel Prize for 2 scientists, Donna Strickland and Gerhard Mourou, who are these 2 here on the right. Here you have Arthur Ashkin, but these 2, they actually achieved what we call chirped pulse amplification, which is a method, an experimental method, which allows you to achieve these very high intensities. So yeah, I work on the field of the Nobel Prize last year. Cheers. So to move on, this is just an example of some work we did recently. Don't worry if you don't understand, but this is focused on interference. So we were looking at laser-induced non-sequential diagonalization, which was viewed primarily as classical. This is a correlated to electron process in a very strong laser field that occurs also very fast. And we found some interference fringes, and we were really happy because people have been looking at this as classical for a long time, actually almost 2 decades. And they have been measured, and there are more measurements coming. So the world is more quantum than one thinks, which is cool when you can think, okay, this is so out of reality, what am I going to do with this? Well, we have also quite a lot of work going on more applied areas. For instance, one example here is the work done by Professor Jonathan Tennyson's group. He's a very prominent molecular physicist, and in this work, they did computations which were really high accuracy, and they could find how much radiation CO2 is absorbing in the atmosphere. In fact, this was orders of magnitude more accurate than what existed before. And this is very good for climate scientists because global warming is a global threat. We need to tackle it, and the more accurate the models are, the better for us. So this is in fact very useful for humanity as a whole, and has a very important and immediate application. But we know also that some people talk and speculate about planet B. So we also have research, and this is a collaboration between the molecular physicists and the astronomers, in which they are seeking for exoplanets. So in this paper, for example, they look at the possibility of habitability. So they found that there was water vapor in the atmosphere of a transiting exoplanet, which means if you have water, in principle, you could harbor life, right? So this is quite an interesting paper. And this is UCL led, and Giovanna Cinetti, she's really involved in this work. Talking about astrophysics, we have also a lot going on from cosmology, from dark matter, from planetary atmospheres, geology, instrumentation. So again, big group. And this is the Mullard Space Science Laboratory. In fact, if you look from the outside, this looks like an old Victorian country house. But if you go inside, you find a state-of-the-art laboratory in which high-precision instruments are designed and constructed. And a lot of stuff which is up there in space, for instance, all these collaborations and the satellites has been built there. And the last group we have is biological physics. It's a new group, has been founded a few years ago. They are very active. They are doing very good work. They are looking at things such as quantum biology. So can you find quantum effects, for instance, in biological structures, or optical tweezers, actually, which was also related to the Nobel Prize this year. Arthur Ashkin was doing something which has applications on there, and also the CPA scientists I talked about, Donna Strickland and Gerard Wu. X-ray diffraction, nanoparticle synthesis, etc., etc. So they are very active. If you want to know more about any of these groups, you can go onto the internet, and you definitely find about what they're doing. And we also have, we are also actively involved in developing the first proton beam therapy center here in the UK, close to the University College Hospital. And this is very important if you want to do targeted, if you want to do a targeted treatment, for instance. If you would do radiotherapy in your brain, you would fry your brain. But if you want to target the tumor and you want to preserve as much as healthy tissue as you can, this would be the way to go. So just to talk about our degree structure, in the first year, you have a lot of core courses, but our emphasis is going to be to put your maths up to scratch, because we have people from everywhere, and there are going to be differences. And we are going to have a lot of maths courses, as you can see. This continues in year 2, but you also have quite a lot of core courses and you start to have optionals. So with optionals, you have the opportunity to tailor your profile to what you would like to do later on in life. For instance, if you are interested in biophysics, you try to get something more in the biology direction. If you are interested in astrophysics, you go for optionals in the astronomy direction. You can also use the opportunity to pick up maths optionals. And in year 3, you're going to do a group project, which is, in fact, a piece of research which is original, and you're going to be supervised by an academic. And finally, in year 4, you have a lot of options, and you have to do a research project, which is a big part of your degree. In fact, 1/3 of the mark of the 4th year comes from there, and is going to be an original piece of research as well. So just to give you an idea of the options for the 4th year, this list, again, is non-exhaustive. It's just really to give you an idea. But as you can see, you could go for advanced quantum physics, atom photon physics, quantum computation, or you can go in the direction of particle physics, which is the yellow one. The purple one is related to interstellar physics and astronomy, etc., etc., etc. So you can have an idea of the breadth that we have here, and I think this is what is important to take home as a message. This would be a typical undergraduate physics timetable. So obviously, this is to give you an example. This is going to depend on room availability and all other factors, but you would have classes in the morning, tutorials in the afternoon. You have also some free time to do your homework, and normally we keep Wednesday free so that you can join societies, do some sport, relax, etc., etc. Because we also think it's important that you have a holistic experience as a student at UCL. So we have physics, theoretical physics, and astrophysics. If you are unsure if you just want to do an MSci or BSc, go for the MSci because it's much easier for us from the administrative point of view to downgrade than to upgrade. And if you are in doubt and you want also to switch your course option, you can do that within the first 3 months because all courses at that time are the same. But after that, it's going to start to branch out. So basically what you have is for astrophysics, you have more time in the observatory. For theoretical physics, you have more maths and more computing. For physics, without anything in front, you have more practical work. So you have to decide until the end of the first term. And on top of that, you have to satisfy the requirements of theoretical physics if you want to move to theoretical physics, which is further maths apart from maths and physics. And here to give you an example, these are entry requirements. You know that because you have already an offer. But what I would like to point out is that all individuals, all applications, they are handled individually. We do have a look at them. And you may be asked to do foreign modern language as a course at UCL. Nobody has ever been rejected for not having that. It's not an entry requirement. Like if you don't have maths, it's a total different story. But nobody has ever been rejected for not having taken a modern foreign language. So we can also offer you the possibility of studying abroad. In fact, UCL runs exchange schemes with a lot of overseas universities. And normally what you do is, if at the end of your first year you're doing really, really, really well, you talk to your personal tutor. And for this, you also have to be in the 4-year option. then we can start to think about arranging for you to go abroad. So you do the first year here, the second year here, you go abroad for the third year, and then you come back for the fourth. This is, however, very competitive, and you really have to be in a very good position to look for that, so you have to have a first. And on top of that, today what we're going to do is, you had the welcome, you had the introduction, so we're going to have a lunch very soon. Then you're going to meet our students. In fact, we're going to have a presentation of someone from the student society, undergraduate student society. Then there will be discussions, there will be a tour, and Steve Fossey is going to provide some information about the University of London Observatory. And today's tour is going to be at the LCN, London Centre of Technology. This changes from time to time depending on the availability, and we rely very much on the goodwill of the research group who wants to open their doors for us. So this varies from open day to open day, and today is going to be at the LCN. So thank you very much for your attention. You can check our website for more information. If you are on site, are there questions? If you are abroad, please use these channels to ask questions. So are there questions? No? Come on. Don't be shy. Now is the time. Ask me anything. Yes?
What are the problem solving tutorial sizes in the first and second year?
Normally around 10 to 15 people. Because we have these big core courses with around 100 people or more. And what we do is we get this big class and we divide into very small groups. And what happens is that the person, not the person in charge, which will be an academic, is going to have this group. And a few days before your exercise sheet will be uploaded on the internet, you're going to give it a try. You should give it a try. And you will see, okay, can I do it, can I not, where do I get stuck, etc., etc. And you're going to meet this person in a small group, and he or she is going to discuss with you, and ideally you should bring your questions. So just say, okay, how about question so and so? Did anybody try? And then you're going to say, okay, I tried, but I got stuck here. And this will help then to initiate a discussion. Yes?
How much credit do you get for the third year for options?
How much credit?
Yeah.
I don't know, actually. But these are normal disciplines as the other ones.
Yeah, because it says 1.5, but when you check the options, it says 15 per option, per topic, so I'm getting kind of confused.
Okay, I don't know. This I have to check. The best person to ask for all these credit details, you know?
The ratio of the weighting of 3 is 1 to 3, something like 135. Yeah, so your first year will count for 9%.
And if you're doing 4 years, it's 1, 3, 5, 5.
Okay.
If you apply for a 3-year degree, but you want to then switch to a 4-year degree, can you do that in the first year?
You can do that, but you have to do it as soon as possible. Okay? Because the other way around, you can do even in the third year. If you are like finishing the third year and you say, I want to downgrade. But this option, 3 to 4, is more difficult to implement, because what happens is in practice, you have all the finances, everything ready to go. So if you have to cancel a bit, it's easier than if you have to add a whole new year. It's really administrative. Yes?
If you want to change subjects, but the subject you want to choose has an admission test, but you're already at UCL, do you still need to take the admission test, or do you get considered?
If, let's say, you are at UCL,
Yeah.
and you are in another course, that's what you're saying.
Yeah.
Okay.
And the course that you want to switch to requires an admission test.
This is not something I'm responsible for, so you have to check with their admissions tutor. And because these things are looked after locally, you see? So my advice would be you contact the person in the department you want to switch your course to and ask, okay, do I have to take this test? What do I have to do? And he or she is going to tell you. And then it's outside the scope of my role or outside the scope of physics. Okay? Now, one thing I do recommend is we get a lot of inquiries, okay, this is very important, from people saying, do you still have a place? I'm doing such and such course and I would like to switch. And sometimes these people are excellent, but we are very often oversubscribed. So say, if you are in economics or engineering, whatever you are doing, and you write and you say, I would like to switch. Sometimes we would even like to take these people in, but we cannot, because we have made a commitment to a big cohort which is coming to study physics. And I don't know where this advice comes from, but a lot of people think they can come and they can switch easily, but it's not that easy because you have to have places in the labs, you have to organize a series of things which you cannot. So my advice is don't try to do it because it's much more complicated than you think. And it doesn't depend on your marks, it depends on places, if there are places available. Depends on your mark, of course, because you have to satisfy the entry requirements, but there are some people who are well above the entry requirements which they have to wait 1 year because we cannot fit them in. So it's very important to bear in mind we have no clearing, we are oversubscribed, usually. Sometimes it changes, it varies from year to year, but it is very competitive. Yes?
With assessment, are you assessed throughout the year or is it just one, like in the summer?
You have just, exams are just in the summer, but for instance, lab assessments and courseworks and problem sheets, these you have throughout the years. Exams are 90% of your results, coursework 10%. Yes?
Does that 10% coursework drop if you choose to do theoretical physics?
No,
Okay.
it's the same.
But it's less lab work.
It's less lab work.
Okay.
Because also if you're doing a theoretical course, you are going to have a problem sheet. Okay, so in the first 2 years you have what we call ICAs, which are tests that you take. But in the third year you have to do problem sheets which you have to hand in. So the ICAs are on site and you come in and you do the test on site. Okay, these are also 10%. In the third year, what you have to do is you have to do homework. So you have to do some exercise sheets at home, typically 3 to 4, and you have to hand them in. Okay? And you have to do this for everywhere. Like for all options, you have this. Yes?
For the theoretical physics course, I'm saying for maths, would it be all right to have like just the AS or does it have to be the...
No, it has to be A-level. A-level. What we have found is that if you have further maths, AAA, the performance is equivalent to have A-star maths, A physics without further maths. Okay? So we, at the moment, settled for further maths, but it could change in the future that you are required then to have A-star maths and A physics without further maths. It's something that is under discussion, but it is just not the same. And this is not anecdotal evidence, this is a study which we actually have performed by looking at the grades of the people. Any more questions? Anything from abroad? No? People are shy today? Okay, there was something. Yeah, someone tried to call me, but yes?
Do the options still remain the same if you study abroad? Like,
You have to do some adjustment, okay? Because normally we pick up the institutions so that so that basically the curriculum and everything, they're compatible. But you will have to do some adjustments. So that's why you cannot have a third year option and just a 3-year option and go abroad, because then your degree would be from abroad and it would be a total mess. So this has to be carefully looked at depending on the university you choose to go. Okay? No questions? Okay, so let's have some lunch. Thank you very much for your attention.